Okay, so we have we said we're going to start with vectors. And we've heard from O level what a vector is. By definition, a vector is a physical quantity that has got both magnitude and direction. So what does that mean? It means that if you have a physical quantity, for example, like what? Displacement. Displacement is different from distance. So displacement is a vector, while distance is not a vector. So it means displacement is the distance you cover in a specified direction. So it would have a magnitude, which is the distance. Then it will also be having a specific direction it's directing you to. If I say, for example, go, when I say go, leave, I'm just asking you to cover some distance away from me. It means you can go anywhere you want. But if I say, leave this house and go to the garage and stay there for the whole day, it means I'm specific. I'm giving you a vector, which is directing you to move from where you are up to the garage. Strictly, you have to move to the garage. So that becomes a displacement. Yeah. So among the examples, we can talk about in vectors, examples of vectors. One includes displacement. Two, we have velocity. You know, we have velocity and we have speed. Eh? So velocity ideally is speed in a specified direction. But if someone just mentions speed, speed is not a vector. But velocity is a vector because velocity takes into consideration the direction where it is acting. Then three, we have what we call acceleration. We also we have what we call force is also a vector. Pressure is also a vector, and so many other items. So, having seen what a vector is, we can look at what we call the notation of vectors or vector symbols. Vector symbols. Now, vector symbols consider the representation of vectors. This is how vectors are represented. Vectors can be represented by one, by an arrow on top, of the vector letter, or with a tilde below the vector letter, i.e., when I say an arrow on top, I'll have, for example, vector AB. It's represented by an arrow on top. It means that is vector moving from A to B. Then if someone has written it like this, with the tilde below it, the tilde is that wave notation kind of notation we have below the wave, below the vector. So it would imply that also you are representing a vector AB in that form. Besides having them, it is just a word ab. But if I want to read the vector AB, then I have to put those notations, n of them, not both. But if you don't put them, you are reading just like you read any other letters combined together. Just like you read is, you read ob, you read of, you read, just like the way you read any other two letters in English. But if you put the arrows and you put those tildes below the letters, or those wave notations below the letters, then you are strictly talking about vectors. Besides that, you are not talking about what? Vectors. So, sometimes also we have them denoted like this. It can be a vector small a, or it can be a vector small a represented by that notation. So if that is the first notation we can talk about to describe the symbols of vectors, they can also tell us to talk about the reverse of these vectors, or the opposite of a vector. If I have a vector A, then the opposite of vector A is going to be a negative of that vector. So it means it is the reverse of A, or of vector A. So if vector A was coming forward, then negative vector A is moving away from the screen. If going to Kampala, from where we are, you are at home, I'm at home. If going to Kampala is from my home to Kampala, then negative going to Kampala is coming back home. That is what it means to have the opposite, or to have a negative of a given vector. It means you reverse the direction of where you have been going. We shall see this applied also in mechanics, where we have relative and resultant motion. And in relative motion, we shall have that concept of negativity of vectors coming into play. So if I had AB, I was moving from A to B, then it means if I was moving from A to B, then the opposite of AB, a vector, becomes a negative AB. Though this negative AB is the same as BA. If A was my home, B is Kampala, I'm moving from A to B, Kampala, but the negative moving from A to B is the same as moving from B coming back to A. So if I represent that with an illustration, you would find that it looks like this. If this is vector A, then this would be negative vector A, reversing direction. The same applies if this is vector AB, then this is going to be negative vector A what? Negative vector AB, which is the same as, because if this is where A is, I am moving to B, then this is the same as A going to B. But this is the same as moving from B going to A. That is why I say these two are the same. Okay? So with those notations, we can go ahead and see multiplication of vectors by scalars among the properties. That is, if you look at properties of vectors, properties of vectors. And the first property is going to be multiplication by a scalar. If I multiply a vector by a scalar, that is, for example, if I have a scalar multiplier k multiplying a vector a, then this is the same as still multiplying that k with that vector a you have. If I have it in terms of a vector ab multiplying the k, this is the same as the scalar multiplier k multiplying vector ab. So you would find that when you're multiplying a scalar multiplier with a vector, you just multiply, it's the same as multiplication, just like you have multiplication of 2 times 3. If 2 is the scalar and 3 is the assumed vector, then you would have multiplied 2 times 3 directly. Then the second one we can talk about is what we call position vectors. And this one we can say is a vector whose reference is the origin, meaning it's a vector that starts from the origin. And among them, for example, it includes vector OP, but this OP can be represented by a small p. You can have vector OQ, whereby this OQ can be represented by a small q. You can have vector OX, whereby this x can be represented by a small x. So that means it is a position vector, but it is referred, or it is beginning from the origin. So it starts from the origin. Then the other definition also should talk about addition and the subtraction of vectors. If I have a vector OP added onto a vector OQ, then I'll have to sum up small vector P plus small vector Q. If it is subtraction, then I'll have to subtract OP take off OQ, then to be the same as small vector P minus small vector Q. So some of these ideas came from O-level or from our ordinary level mathematics, and we can advance some of them here. Then another property we can talk about is the definition of vectors in the coordinate system. The Cartesian coordinate system. The Cartesian coordinate system, sometimes you can say vectors in space. When a vector is in space, what people call corners, sometimes they are not corners. What you call a corner is what you see in your room, the bottom of the floor. The corner you see, there is a line in the room. There is one line coming from up, there is one line going horizontal, there is another line going in another direction on the floor. So that point where those 3 lines meet is what they call a corner. And a corner is a point in space. So that point is in space. So it looks like this, looks like that. with this, which can be the y-axis. This one can be the x-axis. Then this one, we call it the z-axis. With this as 90 to that, with this as 90 to that, and with this as 90 to that. So that point where they meet is the point in space, which we call a corner. Now, these axes define directions of vectors, and vectors that will be moving in the y-axis, they will be represented by a vector j, while vectors that will be representing or moving in the x-axis, they will be represented by a letter I. Then lastly, the vectors that will be moving in the z direction, they will be represented by a letter K. Defined to be moving in these directions, then we say they have what we call the Cartesian units. The Cartesian unit J and K as vectors. These ones we call them the Cartesian units of vectors. These Cartesian units of vectors can be represented further. For example, you can have examples of vectors in space. One, if I have a vector chu, I can call it chu1, chu2, chu3, because these vectors are in 3 dimensions. So I'll have this as chu1 I plus chu2 j plus chu3 k. And these ones we say they are vectors in 3D. You've heard of 3D in movies, ICT, buildings. When they say building is in 3D, most of the diagrams we have been studying from primary. These ones, they're in 2 dimensions, x-axis and y what? But now if you include the direction this side, it goes to 3 dimensions. So your idea is taking it in terms of the x, y, and z coordinate system. And you are taking them in terms of the directions of vectors of I, j, and k. You can have another vector, for example, vector A. Small a is a vector. It can be A1, A2, A3. This type of writing is called the column vector. It's going to be equal to A1 I plus A2 J plus A3 K. Now, when it comes to figures, they can tell you that we have a position vector. In 3 dimensions. Remember, I've already talked about a position vector earlier, whose reference is from the origin. So they can tell you have a position vector OP. Remember, OP is always described by small p. And they tell it is 2, 3, 1. You have a position vector. You have a position vector OQ. which is described by small q, and perhaps it's -1, 5, 4. Maybe you have a position vector OR. This position vector is -1, 0, 4. But this one can be written as -1i plus 0j plus 4k. Because this is 0, anything multiplied by 0 is 0. So you'll find books writing -i plus 4k. So it is you to extract out this vector and confirm how it would have been placed if it was to be written in a column form. Otherwise, some people fail to get to know that 0 is a j, then they treat 4 as the j, then they think the k is not there, but you need to go and analyze. Now, with those illustrations, we can go ahead and look at examples of this, whereby if they can ask you to add or subtract vectors, you can have an example here. Given that a vector A is equal to -i plus 2j plus 3k, and B is given by 4i minus 5j plus 6. They can ask you to find 1, 4a, 2, 3a minus b. 3, can ask you to find a plus b. 4, they can ask us to find 7 into 3a minus b. So when you look at these illustrations, they have scalar multipliers, they have addition, they have subtraction. So they can tell you to manipulate that vector and get us the results. So according to the question, the first question wants us to find Roman 1, 4a. It means 4 is a scalar multiplier, multiplying vector a. But what happens is, if vector a is -1, 2, 3, the reason why we need to always better use column form, we might forget the vector notations. And never in your mind should you combine the vector notations of I, j, k, and then put them in the column. When you write the column vector, you do not need to put there I, j, and what? And k. Now, this 4, you should recall matrices. How do we multiply a scalar multiplier by a matrix? Because now this behaves like a matrix of 3 rows and 1 column. So it means everything has to be multiplied by 4, which is 4 times -1, 4 times 2, 4 times 3. But with time, you don't need to write this. You just need to get the answer straight away as -4, 8, and 12. Of course, some people want to write answers in I, j, and k. They'll want to waste some time here and say it's -4i plus 8j plus 12k. It is okay, but here we've already got the answer. Then the second case, Roman 2, 3 of a minus b. It means multiply vector a by 3, which is -1, 2, 3, and then subtract of vector b, which is 4, -6. You realize we have -3, 6, 9, minus 4, negative 5, 6. This is going to take us to negative 3 minus 4, 6 plus 5, and lastly 9 minus 6. And therefore our answer becomes negative 7, 11, and 7. Sorry, 3. Yeah, as our answer. Then when you come to Roman 3, it's just about addition of the two. One can say vector A plus vector B is the same as negative 1, 2, 3, added on to 4, negative 5, 6. Then this will realize 4 minus 1, then 2 minus 5, then 3 plus what? 6. With this algebra, we shall realize 3, negative 3, and 9. So from these definitions, you realize that what actually is happening is we are adding the i's together, and we are adding the j's together. We are also adding the k's together. It means the only vectors which are supposed to be added to each other or subtracted to each other are those vectors which are acting in the same direction in the on the axis. So if a vector is going this side and it is 2, and there's another vector going this side and is negative 1, these two have to be added as 2 plus negative 1. So the resultant vector in that direction is going to be 1 going in the I what direction. If another vector is going this way in K, which is 7, another is going this way as negative 5, then the resultant of these two will be 7 minus 5, but in the K what direction. I cannot add the 7 to the 1, negative 1. I cannot add the negative 5 to the 2 because they are moving in different directions. If you want to take an example of this, you are in senior 5. There is a student in senior 3. There's another student in senior 1. You cannot sit in the same class to study mathematics. But you can sit with fellow mathematicians who offer math, economics, and you can sit in the same math class where you have math, TD, economics. You can sit in the same math class where you have BCM, biology, chemistry, and mathematics, but you cannot sit in the same class with a P7 chap. You are now in a different direction. The other chap is also in a different what? Direction. So you cannot add vectors of I to those of J. You only add those of I to I and those of J to J. Can you try for me Roman 4? Try for me Roman 4 and give me the answer.
Got negative 49, 77, and 21.
Negative 49, 77, and 41, correct. Okay, let's have another definition. This other definition I'm going to talk about From this, what we have seen, you can note that if I have a scalar multiplier A, multiplying a vector A1, A2, A3, then this scalar multiplier has to affect everything that you have in the bracket. I think I missed noting that. Now, the next definition we're going to talk about is magnitude of a vector. Magnitude of a vector. It is denoted by the symbol. If I write this, it means magnitude of vector A. Then this symbol would mean magnitude of vector B.
Cannot
Magnitude of
AB.
vector, direction vector AB. Okay. So having reached that symbol definition, we can have, now sometimes you need to take either screenshots of this so that you can always recap. But I don't think you can write very fast. If you can write very fast, it's okay. If you can't, you take screenshots, then you do the work again so that it helps you in your review.
I've written down.
Okay. So this is defined by, for example, if you have a vector, if I have vector A being given by A1, A2, and A3, which is the same as A1I plus A2J plus A3K, then the magnitude of vector A is going to be got from the square root of A1 squared plus A2 squared plus A3 what? Squared. So it means it is the root of the sum of the squares of the terms in all directions. And if you want to take a look at that, if you want to have an example, given A1, a vector, is 1, 2, 3, A2 is equal to 6, 7, negative 1, A3 is equal to 1, 0, negative 1. They can ask you to find 1 magnitude of vector A. 2 magnitude of vector A1, that is magnitude of vector A1. Magnitude of vector A1 plus A2. 3, you can ask you to find the magnitude of A1 plus A2 minus twice of A3. All these are vectors. With this illustration, Roman 1 calls for magnitude of vector A1, which is the square root of 1 squared plus 2 squared plus 3 squared. And this will give us square root of 14. And that is the answer. Then for the second case, we need to first get A1 plus A2 before you get the magnitude. This is going to give you 1, 2, 3 added with 6, 7, -1. And this will give me 7, 9, 2. So therefore, the magnitude of A1 plus the magnitude of A2 is going to be equal to the square root of 7 squared plus 9 squared plus 2 squared. And when you simplify this, this will give us 49 plus 81 plus 4 under the square root. 81 plus 4, that's 130, plus 49, that's 130. 130 plus 4, you get 134. So this is square root of 134. You can always get the answers and have those solutions. Unless if it's a very small term, but for those big ones, you can get their decimals.
How many do we round off to?
This is pure math, you can round off to 2, but if it's in paper 2, we can have up to 4 decimal places minimum, unless stated. Okay, so the last one is Roman 3. Roman 3 says the sum of A1, a vector, plus A2, a vector, minus twice of A3, a vector. This will give me 7, 9, 2, minus twice of A3, which is 1, 0, -1. This will take me to 7 minus 2, 9 minus 0, because I'm multiplying 2 times 1, 2 times 0, 2 times -1. Then I will have 2 minus 2. This gives me a plus. So the final answer becomes 5, 9, 4. So the magnitude finally of A1 plus A2, if we have already got the sum of A1 and A2, you don't need to sum them again here. You just extract out that sum earlier on and substitute down here. You'll have twice A3 magnitude. This will give me the square root of 5 squared plus 9 squared plus 4 squared. And my answer will be 25 plus 81, that is 106. 106 plus 16, you get 122. 122 is approximately 11 point something. Eh? So you can always finish it up with a calculator and get those decimals.
11.045.
Okay. Then another definition we need from that, the other definition we can have is a unit vector. This unit vector is a vector whose magnitude is 1. Is a vector whose magnitude is 1. Whereby if you have a vector whose magnitude is equivalent to 1, then we can be in position to call that vector a unit what? A unit vector. So if that is what they call a unit vector, how is it represented? The unit vector can be represented by the symbol with a wave below and a cap on top. And this is the same as the vector of A divided by the magnitude of A. This is the definition for a unit vector. This means this is the unit of vector A, or the unit of vector. Okay, the unit of vector A, we can write it like that. And in this case, they can ask you to maybe find the unit of vector something, whatever is given. Find the unit of vector A given by 4i minus 12j minus 3k. So firstly, you need to determine the magnitude of A, which is got from the square root of 4 squared plus 12 squared plus 3 squared. This will give me square root of 144 plus 25, which is the square root of 169. And the answer is going to be 13. So to find the unit of vector A, it's going to be the vector A itself divided by its what? Magnitude. This will be 4i minus 12j minus 3k, all divided by 13. So the answer becomes 4 out of 13, I minus 12j out of 13 minus 3 out of 13 k. If you want to write it in column form, it's the same as writing it as 4 out of 13, negative 12 out of 13, then negative 3 out of 13. That becomes our answer as well. In column form.
Can you put 1 out of 13 outside the bracket?
Hey, dog, very good. That is if you want to re-extract it out as a scalar multiplier. They can ask you to write it in a scalar product form or in a scalar vector form. You'll have the scalar of 13 out, then you have the 4, then you have the negative 12 out of 13. Sorry, you just have only negative 12, then you have negative 3. Unless if it is asked, but if it is not asked, the 13 should enter the bracket, because you never know if the 13 can be dividing. If it was like 26 out of 13, you know the answer becomes 2. So you need to write the 2 rather than writing the 26 and then the 1 out of 13 outside. So you can simplify as far as possible if the question has not asked you to write it in terms of that scalar. Okay?
Yes.
Yeah. Now, all these definitions we are mentioning, we are going to use them when we come to vectors of lines and when we come to vectors of planes. So we first get these general definitions and have them, then we later on have to introduce lines and planes, which will require some of this knowledge to come back. The next definition we can talk about is the dot scalar product. The dot scalar product of vectors. The dot scalar product of vectors. What does this call for? The dot scalar product of vectors considers two vectors, for example, vector A and vector B. When we dot them, it means we are going to multiply those two vectors. But the multiplication of vectors is not as the way we multiply numbers, that 10 times 2 is 20, 3 times 5 is 15, 6 times 7 is 20, is 42. There is a format which we follow, or there is a definition we follow automatically that brings about the dot product of vectors. You will visit some of the books to see its derivations. Yeah, but right now we cannot, because we are on air, we cannot go much into the details of deriving its proof. But you can visit Backhouse 1 and 2, or even Trant, and find its definition there. Now, given vectors A1, which is equal to A1, A2, A3, and vector B, okay, this is vector A, and vector B, which is given by B1, B2, B3. The dot product of vector A and B, the dot product of vector A and B is given by A dot B. You know, this is where also the dot became a result of multiplication. That's why we can now be in position to use it elsewhere to multiply directly. But in this situation, the dot product is defined as the dot of A and B is given by the magnitude of A, magnitude of B, and the cosine of the angle between them. It is derived from the cosine rule. It is derived from the cosine rule. So I have told you go to Backhouse 1, you'll find that derivation for this expression. So do it as your research. If you don't have Backhouse 1, let me know in my inbox. I'll send you the soft copies.
Yes.
So you should recall that if you don't get the dot of A and the dot of B, we have already seen what magnitude stand for. So the dot of A and dot of B implies that I dot A1, A2, sorry, these are no vectors. We are going to dot A1, A2, and A3. A1, A2, A3, and dot it with B1, B2, and B3. When you dot it with them, we are going to realize this. We are going to dot A1 with B1 plus A2 with B2 plus A3 with B3. And this is going to be our result. So taking into consideration that you know the magnitude of A1 of A is the same as root of A1 squared plus A2 squared plus A3 squared. Then you also know the magnitude of B, a vector, as root of B1 squared plus B2 squared plus B3 what? Squared. Now, why would someone say, why did you only multiply by, someone would ask, why would you only multiply with A1 and B1? It is because if you substitute A1 and B2 and you put them into this equation, this is in the x-axis, this is in the y-axis. The angle between the x-axis and the y-axis is 90. We realized that earlier. Yes? Where is it? Here. The angle between the x-axis and the y-axis is 90. So if I say A1 dotted with B2 it will give me magnitude of A1 times magnitude of B2 cosine of angle what? 90. When it gives us cos of 90 is 0. So the whole of this thing becomes 0. The same applies to A1 dotted with B3. There are also 90 degrees between the two. Times cos of 90, because also this angle here is 90. So for that reason, if that angle is also 90, still it will give you 0. So that's why when you multiply A1 and any other item, if you multiply this A1 with the B2 and B3, they will all give you zeros. That is why we neglect the rest.
Yes.
Okay. So the cosine of the angle between the two vectors, it can always be got. So they can ask you to find the cosine between the two angles or to find the angle between the two vectors. So let's have an illustration using this definition. An example. Given vectors A, where A is 2, 3, -2, B is given by 1, 4, 2, find the angle between these vectors. So the angle between the two vectors is got from the dot scalar product, which we have said is the magnitude of A times the magnitude of B cosine of the angle between them. So you'll have 2, 3, -2, 1, 4, 2 is equal to the square root of 2 squared plus 3 squared plus 2 squared times the square root of 1 squared plus 4 squared plus 2 squared cosine of the angle theta. When you multiply this side is a dot, so it is just 2 times 1, which is 2 times 1, plus 3 times 4, plus -2 times 2 is going to be equal to 4 plus 4, 8, plus 9, which is 17 under the root, times the square root of 16 plus 4, 20, 21 cosine of theta. This will give me 2 plus 12 plus -4 is equal to square root of 17 times 21. Therefore, cos theta is going to be 10 out of root of 17 times 21. So therefore, theta is cos inverse of 10 out of root of 17 times 21. What answer do we get?
$58.04.
58.04. This is acute. They can ask you for obtuse. 180 minus 58.04. What do you get? You get 120. 121. 121.96.
21.96.
This is what?
Obtuse.
Obtuse. If they do not specify whether acute or obtuse, you give both acute and obtuse. If they specify, you give one. All right?
Yes.
Then the other thing is we should note the dot scalar product is always a scalar. It means you don't get a vector. You know, we have been seeing when you add the two vectors, you get a vector. When you subtract two vectors, you get a vector. When you multiply a vector and a scalar, you get a scalar, a vector. But when you multiply, when you dot two vectors, the result is a scalar. That is why when you add this number together, when you add these terms, you get a what?
Scalar.
A scalar. That's why there were no i's, j's, and k's. Why? It's because when you look at them, the unit of I, it's a unit vector. Its magnitude has to be 1. The unit of j, its magnitude has to be 1. Likewise, the unit of k, also its magnitude has to be 1. So when you multiply this I here and the I here, and you get their magnitudes, the answer is 1. So there is a silent one there, a silent one there, a silent one there for all those items. Okay. The other definition we can talk about is perpendicular vectors. Perpendicular vectors. When are vectors perpendicular? What do you know about items which are perpendicular?
90.
90. What is the what do you know about the 90?
Angle between.
The angle between them is supposed to be 90, right? So if the angle between them is supposed to be 90, then it means the angle between them is 90 degrees. So if the angle between them is 90 degrees, it implies that if I dot a vector A and a vector B, I'll get magnitude of A, magnitude of B times cosine of 90 degrees. But the cos of 90 degrees is 0. So it means if you dot A and B, and the answer is 0, then you have dotted A and B, which are perpendicular to each other. Okay?
Yes.
So if I can ask you to show that the vectors A, which is equal to 5, -1, sorry, 5, and then -2 is -2, and then you have 1, and the B which is 2, -4, show that they are perpendicular. It means if you dot A and B, you must get what? A 0. If they confirm that, then it confirms that they are perpendicular. So therefore, 2, 3, -4 dotted with 5, -2, 1. It will give me 2 times 5, which is what?
10.
10, plus 3 times -2, which is -6, positive 6, -6, plus -1 times 4, -4 times 1. This will give me 10 minus 6 minus 4, and the answer is 0. This confirms that they are appendicular. They are perpendicular. Try for me this one. Given that vector A, which is 1, negative mu, and 1, and vector B, which is negative 3, 2, and 4, are perpendicular, find the value of mu. That is yours to try out, so try it out now.
I have.
What have you got?
I have.
Correct. Okay. The second last definition we want to look at is parallel vectors. Now, for parallel vectors, they have 2 items. One, the angle between them is 0 or 180 degrees. Then the other item is one is always a scalar multiplier of another. If vectors are parallel, then one is a scalar multiplier another. I.e., if I have A and is equal to lambda times B, then it means A is parallel to B, to vector B. Also, I've said the angle between them is 0 degrees. So it implies that the dot of A and B is equal to the magnitude of A times the magnitude of B, cosine of 0. But cos of 0 is 1. So that means A dot B is equal to the magnitude of A times the magnitude of B. If you confirm that, then it means the vectors are parallel to each other, any of the two. But this occurs for like parallel vectors. The like parallel vectors are ones that are facing in the same direction. Then we have what we call the unlike parallel vectors. The unlike parallel vectors, one faces this way, the other is facing that way. They are parallel, but they are unlike, not going in the same direction. It means the angle between them is 180. Because you draw the resultants, they will look like this. One goes this way, one goes that way. So you find that the angle between them is 100 what? 80 degrees. So when you have unlike parallel vectors, then the dot of A and the B will give you the magnitude of A times the magnitude of B, cosine of 100 what? So therefore A dot B would be equal to a negative of the magnitude of A and the magnitude of B, because cos of 180 is a negative 1. Show that the following vectors are parallel. Vector lambda 1 is equal to 1, negative 2, 3. Vector lambda 2 is equal to negative 4, 8, negative 12. So when you look at lambda 2, it's the bigger one, it has bigger terms. When you factorize out negative 4, you will get a negative 4 in two brackets. Negative 4 divided by negative 4 is 24, negative 12 divided by negative 4. This will take you to negative 4 of 1, negative 2 over 3. But ideally, this is equal to lambda 1. So this means lambda 2 is equal to a negative 4 of lambda 1. Hence they are what? Hence they are parallel. Then you try it out for me using the definition of magnitude and dot. Try to prove whether they are parallel and tell me the answer you get.
Teacher,
Yes, please.
I'm supposed to use the
You're using this
A
one.
dot-
A dot
yeah,
B and
I'm getting 30 equaling to negative 35.
30 equaling to negative
35.299.
No, it should be giving you negative 30 is equal to maybe 30. I mean, if AB is 30, then a magnitude of A and magnitude of B should be giving you negative 30. Okay, let's check it out. First of all, you get AB. AB, okay, we don't have A and B, we have lambda 1 and lambda 2. Lambda 1 and lambda 2 is equal to 1, negative 2, 3, dotted with negative 4, 8, negative 12. This will give me negative 4, minus 16 minus 36.
Oh, I used 2 instead of negative 2.
Okay, that's where the problem is.
Mm.
So this gives us negative 20, which gives us negative 56. Not so. Then get the magnitude of 1, which is root of 1 squared plus 2 squared plus 3 squared, which gives us root of 14. Then magnitude of 2 would give us root of 4 squared plus 8 squared plus 12 squared, which is root of 144 plus 80. Is it? 64 plus 16, that's 80, right? So it gives us root of 224. So the magnitude of lambda 1 and lambda 2 is equal to root of 14 times root of 224, which is the same as square root of 14 times 224. That's I must give you 56.
Yes.
Get it?
Yes.
Yeah. Hence proof. So 56 is equal to negative 56 because that's what it says up there. Okay, so the last definition for today is what we are going to call the cross product of vectors. The cross product of vectors. Now, the cross product of vectors comes from a definition of a 3 by 3 matrix whose determinant is to be got. If you're given two vectors, A, which is A1, A2, A3, and B, which is B1, B2, and B3, then the cross of vector A and vector B is written as A cross B. This reads cross, doesn't mean multiplication, and it is given by the magnitude of A times the magnitude of B, sine of the angle between them. Furthermore, the cross of A and the cross of B comes from I, negative J, and K of A1, A2, A3, B1, B2, B3, and then we determine its magnitude. This will give us the presentation for this. It means, for example, if I want to handle I, the first vector, then it will give me I, then the determinant of anything not in the row of I, not in the column of I. Then minus J, anything not in the row of J, row of J is this one. Then we have the column of j is here. So you forget anything that is in the j of k in the column of j, which is a1. I'll have here b1. Then I'll have here a3, and I'll have here b3. Lastly, plus k. Anything in k, this row is in k, has k, this column has k. So I will not consider anything in the row of k and anything in the column of k, which will be a1, b1, a2, b2. Then you know that symbol from O level, that means magnitude of a determinant, determinant of a 2 by 2. So this will give me I1 into A2 B3 minus A3 B2 minus J of A1 B3 minus A3 B1 plus K of A1 B2 minus A2 of B1. And then you'll get our result. So let's have an illustration of this so that we can see the relevance of the equation very well. So this is a magnitude. This is a magnitude. Find the cross products of the vectors A is equal to I minus 3j plus 3k. B is equal to negative I minus 3j plus 2k. So you're going to find A cross B, which is equal to I negative j positive k. The value of A is 1, negative 3, 3, negative 1, negative 3 for B up to 2. So if you want to solve this, we shall have I. Anything out of I is negative 3, 3, negative 3, 2, minus j. Anything out of j's column and row, we have 1, negative 1, 3, 2, plus k. K is 1, negative 3, negative 1, negative 3. So giving us I into negative 6 minus 9 minus j into 2 minus 3 plus k into negative 3 minus 3. This will give me I into, this becomes a plus, a 3, minus j, these are vectors. Don't forget the vector notations. Into 5 plus k into negative 6. So it means our cross of A and B has given us 3, negative 5, and negative 6. When they go ahead and say find the magnitude of the cross of the two, you now know how to find the magnitude. Then you say square root of 9 plus 25 plus 36, which is 34 plus 36, and the answer is root of 70. So in this regard, you are finding what we call the cross product. Do you have a question on this?
Yeah, is the j always going to be a negative?
Yes, please. That's the definition.
Okay. Then
That's the
here in
formula.
the final answer, 3, -5, -6.
Mm.
We had 5, -j, then 5. So we bring the negative to the 5.
Oh, wait. This one, we had the what?
No, the answer here is -j, 5. Then writing the column.
Okay. It's the same as writing it like this. 3i minus 5j minus 6k. It's the same.
Okay.
Here, I just want to write it in column form. You know, I told you writing in column form eases the algebra of minimum of risking missing out the vector notations.
Yes.
So basically, those are our definitions for today. I trust you have some of those vector. You have the book for Mr. Walgada, right?
I have the question bank.
You have the question bar. Okay. I'll screenshot for you some numbers to take a look at, for you to try out and see that you have these some of these definitions catered for. Maybe the other note is to remember that if you're given a vector which is a direction vector, the direction vector PQ is the same as OQ minus OP. If I have PR, it is the same as OR minus O what?
OP.
If I have AB, it's the same as OB
minus
OA. So that's knowledge from all levels, though I thought you have it in already. So in case they give you points, point A, B, C, then they ask you to find A, B, B, C, you can always find them by subtraction. Though the second one subtracts the first one. Okay, so we can stop at that for today. Let's meet at 2 for physics, and we see how best we can have everything sorted.
Okay. Thank you.
Okay, see you then.